In this tutorial we're just going to have a look at kinetics, and basically that is how fast reactions proceed and what governs the rate of the reaction and things like that. So if we take this example here where we've got three reactants, maybe one of them doesn't react, we'll find out. Maybe one of them doesn't actually contribute much to the speed at which the reaction goes, and maybe it has a minor involvement, or one has more involvement than the other, and so on and so on. Reaction kinetics helps us to understand this and helps us to understand the rate of formation of our product and the rate of consumption of our reactants. So if we take for example a few terms here, so we take A, B and C as the reactants. We need to know first of all what the order of reaction is, and I'll just briefly explain that. If we take A and we double that, okay, and we're looking at the formation of D, and we just draw a graph. Let me just draw a graph. What colour should I do? Blue, okay. So just draw this graph here. Now this is A, and I'll just draw those square brackets. That means the concentration of A, so I'll just write that. Concentration of A equals that, okay, that's what I've drawn there. So that's what this means, and I'll just move that out of the way actually. Just move this down here for now. So it's concentration of A in the solution, and we want to see the rate at which this reaction goes. Yeah, so we're just going to have a quick look. Does it have an effect? If increasing the concentration, that's going up there, increasing the concentration of in fact I'll put this down here, it's probably best to do it the other way around. If increasing the concentration increases the rate of reaction, then A is taking part in the reaction. So we put on this side here, and I'll put this in red, this is the rate of the reaction, okay? So if we'll keep that blue, if the rate of reaction of A increases, if we double the concentration of A, then the rate increases by 2, then this is considered to be first order. That means if we triple the concentration of A, so if I put that 1 there, if we put 1, then that's 1, that's the rate of just 1 moles added. And then if I put this as 2 here, 2 times the concentration, then the rate goes up by a factor of 2 here, and so on and so on. Okay, I'll put 3 there. 3. Alright, so you can see the general trend there, that increasing A makes this go up linearly. So it has the same effect. Doubling it increases the rate by 2, tripling it increases the rate by 3. Now what would be the effect if instead of being first order it actually didn't do anything? So let's have a look at that. Let's just draw that in light blue here. So if the concentration of A had no effect, I'll put it here, no effect, okay, that's an F, and that's, I'll call this first order. I'll just put that in dark blue, then we can, oops, let's undo that, let's change my arrow. I'm just trying to make it so it's sensible to look at later on. So, and I'll change back to light blue, and I've just changed that back, hold on a second, change that to dark blue, I'll change my pen to light blue. So if the rate of reaction didn't vary, then we'd have something like this. This dashed line here represents this one. So zero order effect, that would be zero order. Okay, this is, so that's zero, write that in brackets, zero order. If increasing the amount of concentration of A actually doubled, for example, if it had a second order effect, and I'll leave it at second order, but I'll draw this in red. A second order effect would actually, as that got to 2 mole equivalents, it would be up here at 4, wouldn't it? So that would go quickly up like this, yeah? And that would be, the reaction rate would increase at the square of whatever the concentration is, and that would be a second order effect. So increasing this by 2 gives it 4 times the rate, and so on and so on. So this is a second order, okay? So we've got zero order, first order, second order, and that's just concentration of A. We can do the same kind of thing, keeping A constant, keeping C constant, so we don't change them. When we look at how fast a reaction is going, we must make sure that these remain constant, otherwise their effect might interfere with the reaction rate too. So what we have to do is just make sure they're constant when we're looking at A, and then we move on to B and we'll look at the effect that B's concentration has, and then similarly we'll look at C. And while we're looking at B, we keep A and C constant, and while we're looking at C, we keep A and B constant, and that's how we find the order reaction. So then that brings us down to this. So just move, so we're getting a feel for how the reactants affect how fast the reaction's produced. And the rate is just basically either the rate of consumption of our materials or the rate of production of our products. So I'm just going to scroll down here a little bit, because now I need to write the rate equation. So the rate, I'm going to make up, is proportional to the concentration of A times the concentration of B times the concentration of C. Okay, I'll just put little dots in there, then you know it's multiplied by. Now what our experiments above have shown, yeah, so what our experiments here will show will be what the order is, okay, and I'll show you where to put that in a second. So this, we've done lots of experiments keeping these constant just to find out what the order is of the individual concentrations. Okay, so I'm going to make it up, just going to make it up. Say this came out at 2, this came out at 1, and this actually came out at 0. The overall order of the reaction is this plus this plus this, and so on. If you add some more, it's all the orders added up together. So that would be, it would have an order of 3. Okay, so the overall order of the reaction would be 3. Okay, so order equals 3. Right, but we got this proportional sign there, so we don't want to do that, do we? And what we need to do is work out what the constant is. The rate constant is called, and that is rate equals some constant, a little k there, times A times B. So that's 2 and that's 1, and because that's 0, that's just times 1, so anything to the power of 0 will be 1, so we'll leave that. That's not actually involved, it's not involved in the rate reaction. So this is the first stage. This is called the rate equation, and that's your rate constant, and this is the order, and I'm going to leave it at that until the next tutorial. So that is a basic introduction to the rate of reactions and reaction kinetics.